Let's look at another example. For a fully developed steady flow of Newtonian fluid in a cylindrical smooth pipe, these are all the assumptions that we need to make. The wall shear stress, tau of W, is related to the pipe diameter d, mean fluid velocity u, fluid density ρ, and fluid viscosity mu. Hypothesize an equation that relates all these variables and identify the dimensionless groups. Again, we need to first identify the dimensions of all the quantities. So the dimension shear stress, well, shear stress has a unit of Pascal. And Pascal is a pressure. The pressure is force per unit area. And force is MA divided by area. And M is the mass M. Acceleration is distance L divided by second square, so time square, e to the -2. And then divided by A, which is L squared, so I have L minus 2. Simplify this, this gives us M L minus 1, T minus 2. Then the pipe diameter D should have length scale. The velocity should have length per unit time. The density should give us mass per volume, so that's L to the -3. And viscosity has a unit of Pascal times second, so the second is time. So we already know Pascal, which is a pressure, has a dimension of M, L minus 1, T minus 2, and now I'm multiplying by T. So I can simplify this as T to the -1. And now, what I can do is to use the Buckingham Pi theorem, which tells us that the number of quantities, which here is 5, n is equal to 5, minus m independent dimensions. Here we can choose the independent dimensions here as L. And something that relates to T, let's choose this. And then something that relates to M. Okay, and mu and tau can be rewritten, are dependent on D, U, and ρ. So M is equal to 3. So that gives us n minus m is 2 dimensionless groups that we can identify. So let's first proceed in identifying the dimensionless groups using the system of equations approach. The first, bidimensional homogeneity. We know that tau of W should be proportional to D, U, ρ, mu, each raised to some power, say A, B, C, and D. Then we can substitute all these dimensions into this equation. So I have on the left hand side m L minus 1 T minus 2 is proportional to L raised to the A. U, the dimension is L T minus 1 raised to power of B. Rho, I have m L minus 3 to the C. And mu, I have m L minus 1 T minus 1 raised to power of D. Now I can group by variables. The variables are m, L, T. So for m on the left hand side I have 1, on the right hand side I have C plus D. For L I have -1 is equal to A plus B minus 3C minus D. And for T, I have -2 is equal to minus B and then minus D. I can rewrite these equations. So the first equation I can rewrite as C is equal to 1 minus D. The third equation I can write as B is equal to 2 minus D. And the middle equation, I can substitute everything, and let's say we have A is equal to minus 1, then B is minus B, but B is 2 minus D, plus 3C, but C is 1 minus D, and finally plus D. Let's solve this. If I can do the math, this is minus 3 plus 3, this cancels out. And then we have plus D minus D, that cancels out. Sorry, we have plus D minus 3D plus D. So this is minus D. And with all these equations, we can substitute these back to the original equation, which gives us tau W is proportional to D to the A, where A is minus D, U raised to the power of B, which is 2 minus D, rho to the power of C, which is 1 minus D, and mu to the power of D. Now we can group by exponents. It's either constants or D. So tau W is proportional to anything that's with D, which is D to the minus 1, U to the minus 1, rho to the minus 1, and mu raised to the power of D. And the constants are U to the power of 2, rho to the power of 1. And we can move these constants to the left. So we have divided by U2 and rho. So this is the equation that relates tau W with all other variables. And the dimensionless groups that arise from this is tau of W divided by U squared of rho raised to some arbitrary power. And if I rewrite this, it can be mu divided by D, U, and rho raised to some other arbitrary exponent. If you are stressed out solving these systems of equations, I'm with you. So let's try another method using the stand-in variable. To solve this with stand-in variables, we still have to do the dimension analysis and the Buckingham Pi theorem identifying we have two dimensionless groups. The hardest part actually is to identify a good stand-in variable or good stand-in variables that we will be using in solving this problem. So we start by identifying any base dimensions. So here we have a base dimension L, so we will use that as the standing variable for length. And now we need a standing variable for T and M. We see that there are multiple options for M. Rho, mu, and tau W all has M's, but what is the simplest? The rho is the simplest because it only has an additional L. It doesn't relate to T. So I'll choose that as the standing variable for M. The same goes with standing variable for T. I can choose tau W, U, or mu, but only U is related to L alone, not M. So I'll choose it as the standing variable for T. And after that, it will be all easy work like solving a puzzle. So for example, we want to non-dimensionalize tau W, which has a dimension of M, L-1, T-2. So note that we want to save the dimension, base dimension L to the last. because the other base dimensions, L and M, all contains L. So if we do L first, we still have to deal with it later. So let's do instead T first. To make T disappear, so first I write down the standing variable's dimension, which is Lt to the minus 1. To make T disappear, I want T minus 2, it should be multiplied by T to the second. And how to make this T to the second? I raise this to the power of minus 2, so that this gives us T to the power of 2. So we have determined the power should be minus 2, and the standing variable is u. Okay, now I can deal with the base dimension m. Here I have a base dimension, here is m, so to make it disappear, I want something that has m to the minus 1. So the standing variable has a dimension of m, l minus 3. So to make m of minus 1, I'll raise this to the power of minus 1. So that m and m minus 1 cancels out. And then this is having the standing variable of rho. So I'll raise rho to the power of minus 1. And finally, I'll deal with L. Here I have L to the minus 1 times L to the minus 2 and multiply by L to the positive 3. So this is L to the 0. So it already non-dimensionalized itself. So here we have arrived at our first dimensionless group, which is tau w divided by u squared times rho. Now we can work with the second dimensionless group that stems from mu. So mu has a dimension of m, l minus 1, t minus 1. Okay, still we want to save l to the last because t and m's standing variable has dimensions of l as well, so it will mess things up. So let's first consider t. Okay, so the question is, what power do I need to raise u to? And we need to determine that using t. We already have a t minus 1. I want t to the first. So the exponent, I want a minus 1, so that minus 1 multiplied by minus 1 is positive 1. Okay, so this cancels out, and I should raise u to the minus 1. Next, I'll handle m. So m, the standing variable is rho, and has dimension m, l minus 3. What power should I raise it to? I already have a m raised to the power of 1. What I want is an m raised to the power of minus 1. So I'll just raise the whole thing to minus 1. So this cancels with this. So rho is minus 1. Finally, I'll deal with L. So L, I have L minus 1. Here is also L minus 1. Here I have a L raised to the power of 3. So I already have a L to the first power. So now I can finally deal with the standing variable for L. So now what exponent should I raise it to? So to cancel this, I want something that's L minus 1. So I just raise to the power of minus 1, and the standing variable for L is D. And we have arrived at our second dimensionless group, which is mu divided by u rho d. And this can be raised to any arbitrary power, this as well.